And we're back. Today we're going to continue with our covalent bonding lecture. Before you guys get started, here is our assignment for this It's going to be let's get recalibrated here. There we go. It's going to be page 220, number 7 and 8, page 225, numbers 9 and 12. Okay? And this is the nature of covalent bonding. All right, covalent bonding, electron sharing occurs so that atoms attain the electron configurations of noble gases. Okay, this is also known as the octet rule that we've been talking about before. Okay, so that in order for our atom can get this electron configuration, this full 8 electrons, our nonmetals will start sharing electrons. Okay, and single covalent bonds occur when two atoms share a pair of electrons. Right, and the way we show this is through our Lewis dot structures, also known as electron dot structures. Okay, and this is our method of demonstrating the valence electrons in an atom, an element, or a compound. Okay, so there are certain steps to making our particular drawings. Okay, our first step is we determine the number of valence electrons that are available for the structure in a compound. So we just count out how many valence electrons any particular element has. Okay, and then we add them all together and we know that's what's available. Okay. The second step is we arrange the atom so that carbons are centered in the compound and hydrogens are on the outside. Other nonmetals can also be in the center or outside of the compound. Now, this follows a particular rule that I want you to write over here on the side of your notes. And it's this. It is the honk rule. H-O-N-C. And so we're actually going to go to another page, and I want you to write this as best you can in the side of your notes over here. So here we go to the other page to describe the honk rule. Okay, so here's our honk rule. Okay, so here's our honk rule. H-O-N-C. Here's how it works. Hydrogens go to the, now H stands for hydrogens and halogens. Hydrogen and halogen. Okay. O stands for the oxygens. N stands for the nitrogens. And C stands for the carbons. Okay, and so by the oxygens, nitrogens, and carbons, I mean their families. So everything in the oxygen family, everything in the nitrogen family, and everything in the carbon family. Now, when we are building our chemicals, we start with the carbons. Carbons will always be on the inside, or in the center of your molecule, and hydrogens will be on the outside of your molecule. Okay, and there's a reason for this, and this has to do with the number of bonds that they can actually make. Okay, carbon, because carbon looks like this, and it's got 4 electron dots around it, has 4 valence electrons. I realize that this is not the actual way to draw a carbon, the carbon dot structure, because we're supposed to do the first 2 together. But for covalent bonding purposes, this is how we need to do it. We separate our 4 electrons. Carbon will then have 4 bonds, or it has 4 sites on it where it can make bonds and it can share electrons with other things. That's because it needs 4 electrons in order to make its octet. Nitrogen looks like this, okay, with 5 electrons, and it has 3 sites where it can bond, and so its honk number, for lack of a better word, is 3 bonds. Okay, oxygen makes 2 bonds, and the hydrogen and halogens all make 1 bond. They all only need one electron in order to bond. So this rule, HONC, honk, okay, also follows the 1, 2, 3, 4 pattern for our number of bonds that it can make. And the more bonds it makes, the more towards the center of the molecule it's going to be, which will kind of make sense once you start practicing these, because you want the more flexible atoms to be in the center of your structure. So let's get back and let's try and make some more of these. And here we are. And so let's try our first ones. Let's try hydrogen here. So the first thing we're going to do is determine the number of valence electrons available for the structure of the compound. Well, that would be, here's hydrogen. Each hydrogen has one electron, and so there would be two hydrogens and one electron for a total of 2 electrons. Now let's also look at the honk rule. Hydrogen, there are two hydrogens. Each hydrogen needs one bond. So 2 hydrogens going to equal 2 bonds. Now, something to keep in mind here is that when you have an atom, let's say you have an atom that needs a bond. So atom A needs one bond. Okay, and it's going to bond with another atom A that also only needs one bond. Well, since these two are sharing the bond, this counts for both atoms. So however many bonds that we have from our honk rule, we can divide that by 2 because we know that there's going to be an atom on either side of that bond. This tells us that between H2, between our two H's, that there's only going to be one bond according to our honk rule. And so this is what H2 is going to look like. You're going to H here. You're going to have one electron from each of the H's, and then you'll have another H. And voila, that is your H2 molecule. So let's try the same thing over here with chlorine. We will erase our math over here, and we'll try this again with the chlorine. Chlorine has 7 valence electrons, and there's two chlorine atoms. So 2 times the 7 valence electrons is 14 electrons that we're going to draw in our dot structure. However, chlorine is also a halogen, and its honk rule means that there are 2 chlorine atoms. Each one needs one bond, so that's a total of 2 bonds. In fact, we're going to write this over here. 1, 2, 3, and 4 for our honk number. Okay, so we will divide that by 2 again because each chlorine gets to share their bond, and that's a total of 1 bond again. Well, interestingly, we only needed 2 electrons for this bond over here, but here we're going to use 14. But that's okay, because once we draw these out, we'll see that chlorine, because chlorine isn't going to try and look like helium like hydrogen does, chlorine is going to try and look like argon. So to look like argon, it needs to have all 8 of its valence electrons. And there you go. You have chlorine with a single bond in between, and you have all 8 of its octets right there for that chlorine. And you have all 8 of its octets there for that chlorine. And these 2 in the middle are the ones that are shared between the 2, and that is your covalent bond. So let's try methane here. Methane is the next one. Methane is CH4. CH4 has, so let's find, step 1, let's find our valence electron. Carbon has 4 valence electrons. Each hydrogen has 4 valence electrons. And so 4 plus our 1 times 4 is a total of 8 electrons. Now let's look at our honk number. Carbon has 4 bonds. And we know that each hydrogen also needs 1 bond. So 4 times our hydrogen also equals 4 bonds. So actually, there's going to be 8 bonds that we need to account for. We divide it by 2 because they share, and that equals 4 bonds in the structure. So we're going to have carbon in the middle, because carbon always goes in the middle. We have 8 electrons, so we're going to draw our octet for our carbon. And then our hydrogens are hooked up to those pairs of electrons, because those are bound to our carbon here in the middle. All right? Here's carbon tetrachloride, and it's very much the same thing as these guys up here, except with carbons in the middle. We do the math. Carbon brings 4 electrons. Each one of the 4 chlorines will bring us 7 electrons. So that's a total of 4 plus 4 times 7 is 32. We do our honk number, however, okay, and we wind up with something different. Once again, calcium has 4 bonds, but chlorine, again, is a halogen, and chlorine only has 1 bond. So 1, 4 times each chlorine, again, only gives us 4 bonds. We add those together, we get 8 bonds. We divide by 2 because they share, and we wind up with needing 4 bonds again. And so our carbon is going to be in the center with a chlorine, and a chlorine, and a chlorine, a chlorine, down to it, all the way around here. And that would be all 32 of our electrons. It's kind of tough to see, but if you look real closely, you can see all the electrons around the carbon, around the chlorine. Okay, which brings us to our last one. Let's try this one. Okay, so we look at our last few. Here is, this is ethane, C2H6, and let's do these numbers again. There's 2 times 4 for your carbon, that's your total number of valence electrons, plus 1 for every hydrogen, that's 2 times 4, plus 6 times 1 is a total of 14 electrons. We go by our honk rule, there's 2 carbons, so it's 2 carbons equals 8 bonds, 6 hydrogens equals another 6 bonds. It's a total of 14 bonds. Divide that by 2 because they share. And that winds up with 7 bonds that we're going to need to drop. So we're going to have 2 carbons in the center. They are going to be bound together. Then we have the other pairs of electrons that represent bonds. Around those, and you put hydrogens everywhere. And there you go. You have you have 6 hydrogens around your carbon. Yes, I had to shrink that up a bit because we were running out of space. Now, sometimes we have unshared pair electrons. Most of these are either fulfilling the octet or they're distinct electrons in here, but sometimes we have to pay attention to unpaired shares of electrons. All right, so one's going to be here with water. If we're going to draw water, oxygen winds up being like this. Okay, there's an oxygen, and it has 6 valence electrons around it. Here. And hydrogen each has 1, so I'll even draw those in different colors so you can see where they're coming in. Here's a hydrogen, and here's a hydrogen. Now, these guys over here are lone pairs, okay, or unshared pair electrons. Okay, these lone pairs, keep an eye on them. They'll become much more important later on. NH3 does the same thing. It's going to look like this: N, 1, 2, 3, 4, 5, and 3 hydrogens. H, H, H. Voila, and there is another lone pair. Okay, so that's how we do our single bond covalent molecules. We will get a little bit more complicated next time when we start talking about double and triple bond molecules, but the math is pretty much the same. And if you're getting a good hang of this, then the next page should be relatively simple for you. So we'll see you guys next time.